This course on lubrication and bearings comes from the 4th class maintenance Pan Global, Part B, Unit 1, version 3.0. The two chapters being covered will be the lubrication principles and the type of bearings and lubrication. Friction. Friction is the resistance to motion. When two surfaces are in contact with one another, the microscopic irregularities on the surface will actually lock the two surfaces together, hindering any motion between those two surfaces. Lubrication separates contacting surfaces moving in relation to each other. This separation is achieved by adding a substance between the two surfaces, and that substance is called a lubricant. Lubricants have 6 purposes. Friction reduction and wear reduction are the two primary functions of a lubricant. Remember those for your government examination. Corrosion control, shock absorption, sealing, and temperature control are also purposes of a lubricant. Friction reduction. When two surfaces are rubbing together, the little peaks and valleys are coming in contact with one another and causing a resistance to motion. By adding a lubricant between those two surfaces are separated and the friction is greatly reduced. Wear reduction. When two surfaces are rubbing together, the high spots will actually collide with one another, breaking off some of the material. In some instances, the breaking off of material will actually cause a polishing action to make the two surfaces smoother in relation to one another. In other cases, the collisions may actually break off chunks of material, and instead of polishing and making a smoother surface, it can actually leave a rougher surface with more irregularities, and in that case, wear will increase. Corrosion reduction. Lubricants form a corrosion barrier film on the metal surfaces. When lubricants are exposed to oxygen, they will form oxides and acids which attack bearing metals. Temperature control. The amount of force required to overcome friction will produce heat. If the amount of heat is uncontrolled, that can cause a high temperature condition inside bearings. And potentially that high temperature can cause some negative repercussions. It can cause your bearing materials to lose strength, hardness, and also the ability of the lubricant itself to support load. If you have a large amount of heat that needs to be taken away from a bearing, we can circulate larger volumes of lubricant, and that heat can be carried away from the bearing and discharged into a heat exchanger of some sort. Shock absorption. When two surfaces impact each other, lubricant acts as a cushion to absorb the shock. This type of action happens on the face of all gears when they come in contact with each other. Sealing. Lubricants are used to provide a seal between moving surfaces such as rotating shaft seals and also piston and cylinder walls. When looking at the classes of lubricants, many things have to be considered. What's the nature of the surfaces that are going to be lubricated, the load that's going to be carried, the speed that it's going to be used at, the operating temperature. And when we look further at our lubricants, we also want to look at the minimum coefficient of friction, how well the lubricant will actually adhere to the surfaces, how chemically stable they'll be, how resistant they are to oxidization, and also emulsion, and also the fluidity at low temperatures. When we look at the classes of lubricants, they fall into 3 general categories. They are solid lubricants, semi-solid lubricants, and liquid lubricants. With solid lubricants, they're suitable for high loads and extreme temperatures, and also when there's going to be chemical contact with the lubricant. Some of the materials that are used are graphite, soapstone, molybdenum disulfide, mica, and polymer films. These lubricants are applied by rubbing or polishing them directly on surfaces. They may also be mixed with a liquid, such as an oil. They may also be mixed into a bonding agent and sprayed on. Semi-solid lubricants are commonly known as grease. Grease is made by taking a liquid lubricant and mixing it with a thickening agent. The thickening agents are referred to as soaps. Greases are used in applications where oil would leak away, or also where oil may splash or contaminate products. You'll find that greases are used in ball and roller bearings. A place where grease is not suited are places where a bearing will generate large amounts of heat, and that heat needs to be continuously carried away. Grease will also provide a seal from dirt and water entering bearings. Grease can provide a protective coating that will not easily drain or wash away. The characteristics of a good grease are purity, consistency, chemical stability, and tenacity. These characteristics are provided by the thickening agent, or soap. Calcium-based greases. They are the most commonly used greases, and they're also the cheapest to purchase. The calcium-based greases can be used in a variety of applications. They're used in grease guns, for cup grease, axle grease, water pumps. Calcium greases are not soluble in water, so therefore you can use them in damp conditions. The downside to a calcium-based grease is they're only good at up to 70 degrees Celsius. Above 70 degrees Celsius, the thickening agent soap and oil will separate. Sodium-based greases are more sticky than a calcium-based grease. They're also good to higher temperatures. They'll go as high as 120 degrees Celsius. Sodium-based greases are often used in high-speed roller bearings. Sodium grease is water soluble. Due to that fact, they are not suited for wet conditions. With mixed base greases, they combine the characteristics of both sodium and calcium-based greases. Calcium will increase the insolubility of water, while the sodium will increase the temperature range of the grease. The mixed base greases withstand higher temperatures than calcium and resist water to some degree. Barium and lithium-based greases use either barium or lithium as their thickening agent. The uses are water-resistant applications, also high-temperature applications. They're good for ball and roller bearings, and some lithium greases are suitable for low temperatures, such as minus 55 degrees Celsius. Aluminum-based greases are very good at resisting water and also very sticky. They stick to surfaces very well. So the uses for the aluminum greases are for temperatures up to 80 degrees. They're very good for rust protection because of the stickiness. Remember that for your government examinations. Aluminum grease, very good for rust protection because it's sticky. Places where you do not want to be using aluminum-based greases are high-speed applications where that actual stickiness of the grease itself would actually generate a lot of heat. Specialty greases are mineral oils that are thickened with solid lubricants. The solid lubricants that are used are graphite, mica, and talc. These are used in heavy load, slow speed applications such as tractor rollers, cement mixers, and heavy equipment. The classes of liquid lubricants. Liquid lubricants come from three sources: mineral oils that are produced from crude petroleum, fixed oils, also called fatty oils, that come from animal or vegetable origin, and synthetic oils. They are the polyglycols and silicones. Mineral oil is the most widely used of the lubricating oils. It's produced from crude petroleum. When the crude oil is brought into the processing plant, all the light products are taken off first, and the heavier products are left behind, and they are classified into different grades of lubricating oils, where you get the lighter oils from the top of your fractioning column to the heavier oils that are coming off of the bottom. Fixed oils, are also known as fatty oils, originate from animal or vegetables. Some of these can be lard, whale oil, castor oil, cottonseed oil, canola oil. The fixed oils themselves are not used, but actually are mixed with either mineral oils or greases for special applications. They're called fixed because they are non-volatile. Synthetic oils include the polyglycols and silicones. The use of synthetic oils are high temperature applications with high resistance to fire for turbine applications, also resistance to oxidization and sludge formation. When power engineers deal with lubricating oil, a list of properties comes to the forefront. Those properties are viscosity, viscosity index, pour point, flash point, fire point, neutralization number, carbon residue, and flock point. Viscosity is the resistance to internal deformation or shear, and this viscosity will determine the ability of a fluid to flow, also the ability of the fluid to support a load, the power loss due to internal friction, and the heat generated from that internal friction. Just remember that definition for viscosity for your government examination. Viscosity is the resistance to internal deformation or shear. The viscosity index is a measure of how much a viscosity will change over a temperature. A oil with a very low viscosity index will actually change its viscosity quite a large amount from its cold state to its hot state. When you have a oil with a high viscosity index, the viscosity will not change as much from its cold temperature to its high temperature. A good parallel to this, or a good way to illustrate this, is the automatic transmission fluids in automobiles. The viscosity is very consistent from when it's at its high temperature operating range down to its cold start sub-zero operating range. Pour point of oil is the lowest temperature at which an oil will flow. When you look at refrigeration oils, they have to be able to pour at a very low operating temperature. So oils with a low pour point are good for cold climates. Flash and fire point. The flash point is a temperature at which a liquid will give off enough vapor to momentarily ignite, but it will go out. The fire point is a temperature at which a liquid will give off enough vapor to burn continuously when it's ignited. The flash and the fire points are important because they will indicate the temperature at which a fire or an explosion may occur during operating conditions. Neutralization number indicates the acidity of oil. Over time, oil will become more acidic due to the oxidization of the oil. The ongoing neutralization number checks will form a basis for when to have an oil change. A carbon residue test will subject an oil sample to high temperatures and measure how much carbon residue is left behind. When considering oils for reciprocating engines or compressors, a desirable characteristic is to find an oil with a very low carbon residue. The flock point is the temperature at which wax and other suspended particles will settle out of an oil. In lubricating oils, additives can be used to help enhance desirable characteristics. Antioxidants decrease the amount of oxygen combining with oil. That will help reduce the amount of acidity of the oil, and that will prevent corrosion, varnish, and sludge. Detergent dispersants keep substances in suspension so that they do not form deposits. Viscosity index improvers will help to reduce the viscosity change with temperature. Anti-foam additives cause the collapse of bubbles to reduce foaming in oil. Pour point depressants lower the pour point of the oil and remain fluid at a lower temperature. Corrosion inhibitors form a protective film on metal surfaces. In turbines, the oil is the lifeblood of the turbine. It acts as a lubricant, it's also a cooling medium, and it's also used as a sealing medium in hydrogen-cooled generators. The characteristics of a good turbine oil is that it separates easily from water. It'll have corrosion inhibitors, anti-foam and antioxidant inhibitors. Synthetic fire-resistant oils are used to reduce the risk of ignition with nearby high-temperature surfaces. When selecting air compressor cylinder oils, consideration has to be taken so that it has a suitable viscosity at operating temperature of the compressor. The oil should have low carbon residue to prevent deposits of carbon on valves and cylinder walls. Also, the lubricant should be compatible for the cylinder walls and the bearings of the machine. In internal combustion engines, the lubricating oil must be able to withstand the high cylinder temperatures, but also it must lubricate the bearings at lower temperatures. This is a pretty extreme balance, so the oil for internal combustion engines have to have a high viscosity index and also antioxidant and detergent dispersants. That way the oil will not go acidic, and also any contaminants or things that are in the oil, instead of having them settle out and forming deposits, a detergent will keep them in suspension so they can be circulated through filtration or separating equipment. The oil must also have corrosion inhibitors. Refrigeration compressor oils have to have a low pour point. They also must not chemically mix with the refrigerant. And when selecting a compressor oil, a higher viscosity has to be used because some refrigerants such as Freon will actually mix with the oil and make it less viscous. Whenever you hear the term miscible with oil, that means that the refrigerant will mix with oil. It's miscible. When selecting oil for gear lubrication, you can have enclosed gears. That's gears that are inside a casing, and you can also have open gears. So if you have enclosed gears, you want an oil with a low viscosity. That'll reduce the power losses due to the oil drag, and it'll also prevent excessive heating due to the fluid friction. When you have open gears, that's when you want to have a high viscosity oil so that the oil will cling to the surfaces and will not easily wash or wear off. Extreme pressure additives may be used for heavy loaded gear lubricant. We will now look at the two types of lubrication. There's boundary lubrication and fluid film lubrication. With boundary lubrication, the surfaces are separated by a microscopic film of lubricant. And between those surfaces, there will be a certain amount of metal-to-metal contact. So for slow speeds and heavy loads, a grease would be a better choice for a lubricant rather than just plain oil. In special conditions, solid lubricants would be used. Fluid film lubrication is also called flood lubrication. And the way that fluid film lubrication works is the journal must be flooded with a lubricant, and the internal shaft has to be rotating, and the rotating speed will have to be great enough to actually cause a hydraulic lifting action. The hydrodynamic wedge lifting action separates the surface of the journal and the shaft so that there is no physical contact. The oil is the only thing supporting the shaft in the journal. In this slide, we're going to look at fluid film lubrication of a journal bearing, and these four diagrams are going to express the stationary and startup and full running conditions of the bearing. So in the diagram A, the shaft is at rest. It's stationary right now, and the shaft is sitting on the bottom of the journal bearing. And you can see that the center line is below the center line of the bearing itself. And right now there's no oil being delivered to it. It's just static and at rest. In example B, there is oil being delivered to the journal bearing, so it's flooded with lubricant. And the shaft is just starting to rotate. And you'll notice the pressure area is off to the left-hand side. What that is literally the shaft is trying to roll itself up the side of the journal bearing initially. So it's going from a state of boundary lubrication only in A, and in slide B, there's still boundary lubrication, but as the shaft starts to rotate, it's actually going to pull molecules of oil underneath itself to help suspend itself away from the journal bearing. In slide number C, the shaft is rotating, but you'll notice now is the shaft is actually floating off of the bottom of the bearing, and the pressure area is slightly off to the right hand center. Oil is still being delivered, the bearing is still flooded. So right now the shaft is rotating at a great enough speed so that the oil is being pulled underneath the shaft and floating the shaft up. It's actually a hydraulic wedging action. It's hydrodynamic. And when the bearing is up to full speed, the shaft will still be slightly below center, but it'll be slightly to the right. Pressure area will also be slightly to the right, and that's just due to the friction and the pumping action of the oil going between the shaft and the journal. Shell or sleeve bearings are fluid film bearings. They're constructed of a cast iron or a steel housing with a white metal alloy lining the surface. This white metal is very soft. We've referred to it as also babbitt, and this soft white metal deforms to conform to the load conditions. And also the softness of this white metal allows the surfaces to wear in and polish themselves to a more smooth condition. Now, why you would want to have this soft white metal? When your machine is stopped and at rest, there's no fluid film lubricant to suspend the surfaces of the shaft and the bearing itself. So when the machine is at rest, you will have only boundary lubrication, and you'll have some metal to metal contact. That's where that thin white metal comes in. It's there to deform and conform to the shaft. One thing you'll note also in the previous slide is that oil is introduced on the low pressure side of the bearing, and in this case the oil supply would come in from the top. So the oil is always being supplied on the low pressure side of a bearing. It's not going to be introduced underneath the pressure area where that hydraulic wedging action is going on. In shell or sleeve bearings, there's three different methods to lubricate. There's manual feed, automatic feed, and a ring oiler. With the manual oil feed, someone comes along with an oil can, puts a few drops in from typically the top of the bearing, that's the low pressure side, and they'll put a few drops into the bearing, and that will help to coat the surfaces. You can also have an automatic oil feeder, and you'll see these in many different areas of the plant. In our shop downstairs, you'll see lubricators on the side of pumps and on different bearings. So again, you can see a reservoir, and that reservoir is kept with some level of oil inside it. Ring-oiled sleeve bearings utilize a large ring resting on the shaft that will actually rotate in the same direction as the shaft, and the rotating ring will dip into some lubricating oil, pick up the oil, and rotate further and deposit that oil on top of the shaft. And that oil that's deposited on the shaft will then be distributed throughout the sleeve bearing. As the oil circulates through the sleeve bearing, it will eventually drip back into the oil reservoir, and the cycle will repeat. In shell or sleeve bearings, oil is introduced at the low pressure side of the bearing. That typically is on the top side of the bearing. As the oil is introduced into that low pressure area, oil grooves are used to distribute the oil evenly across the surface of the bearing. That way you get a nice smooth coverage of an oil film. There are a few things to note whenever you're looking at oil grooves in bearings, and that is they do not have sharp edges. The edges of the oil grooves are all radiused and smooth, and what that does is that helps to actually lay down a nice smooth layer of oil. If those edges were sharp, instead of laying down a smooth layer of oil, that sharp edge would tend to actually squeegee off the oil and not lubricate very well. The last point about oil grooves is when you look at the design of an oil groove, they never go right to the edge of the bearing. They usually stop a few millimeters away from the edge of the bearing. And that's just so that you can contain the fluid film oil inside the bearing. On the lower half of the bearing, underneath where there's the pressure area that's holding up the entire machine and the shaft, there are no oil grooves in the pressure area. There's only bearing material to support the load. In a plant, when the operators are checking equipment, they're checking for changes in sound or noise and temperature. And those are the clues of the health of bearings. Are they noisy or are they starting to run hot? So 6 of the possible causes of bearing failure are using the wrong viscosity oil. Viscosity might be too high or too low. Poor bearing clearance or oil groove design. If bearings are a little bit too tight, if the clearances are too tight, you can have metal to metal contact and potentially a seize. And if the oil grooves are designed poorly, you may not get a nice film coverage and you could have oil starvation problems. Shaft misalignment, corrosion or metal fatigue, oil or lack of oil. And that seems pretty straightforward. If there's no oil or a lack of oil to a bearing, that's going to be a possible cause of failure. And also, if the oil temperature is too high. When a bearing is generating heat, that heat has to be conducted away from the bearing or overheating will occur. So if the amount of heat being generated by the bearing is greater than the amount of heat being lost to the surrounding air, you may want to water cool the bearing. So there's 3 methods of water cooling, and those 3 are circulating water through jackets that are inside the bearing, installing a cooling coil directly in the oil reservoir of a bearing to help take the heat out of the lubricant directly, And the third is to have an oil circulating system, so oil is circulated through bearings, and the heated oil that's coming out of the bearing will then go through a heat exchanger and then circulated back in. To regulate temperature in water-cooled bearings, there's a few things that can be done, and those are to increase or change the flow of water to the bearing, to switch over to a standby oil cooler, and also to put additional coolers into service. Sometimes bearings will run very hot and emergency bearing cooling will be needed. There's a few choices you have available. You can try to direct some cool air across the bearing to help reduce its temperature. You can use an air hose if you have an adductor, or you can make an adductor. That's to help get a larger volume of air blowing over top of your bearing to help reduce the temperature, to help shed some of the heat off of the bearing to bring it back into operating range. Another option, if it's available to you, is to reduce the loading on the bearing. That will reduce the amount of heat going in. Another thing is to water cool the bearing, and be very careful when you are doing water cooling. You'll take a cold or a cool water and direct the water onto the shaft beside the bearing. Never put the water directly on the bearing. That would be a very bad scenario, and this is the reason why. If you end up cooling the housing of the housing will start to shrink, and that shrinking of the housing will cause tighter bearing clearances, and tighter bearing clearances make more heat or even cause seizures. So you want to be cooling the shaft adjacent to the bearing. We will now look at the forces on bearings. So there's two types of forces acting on bearings. Those are radial forces and axial forces. Radial forces are primarily the weight of the shaft and whatever the machine is acting perpendicular to the axis of the shaft. The bearings are known as radial bearings. Axial forces act parallel to the rotating axis of a machine shaft. So that type of axial force is referred to as an axial thrust, and the bearings that help to handle the axial forces or the axial thrust are called thrust bearings. So the radial thrust is perpendicular to the shaft, and axial thrust is parallel to the shaft. There are three types of thrust and radial bearing designs, and they are the plain sleeve or shell bearings, anti-friction or roller bearings, and tilted pad bearings. The purpose of a thrust bearing is to prevent movement in the axial or lengthwise direction. And there's different styles of thrust bearings. And the first style is the collar thrust bearing. The collar thrust bearing is a very simple bearing where the actual thrust collars are part of the shaft, and there's no oil wedge to support the load, so there's only boundary lubrication. So with this style of thrust collar, it can only handle relatively small thrusts. The next two thrust bearings are both oil wedge style bearings, which are the Mitchell tilted pad type and the Kingsbury tilted pad type thrust bearing. And the last is the ball thrust bearing. In the tilted pad style thrust bearings, you have the Mitchell and the Kingsbury thrust bearing. The way that a tilted pad bearing would work, first and foremost, the entire thrust bearing must be flooded with oil. It has to be fully flooded. Once you've got this fully flooded chamber, you have a rotating collar, and that rotating collar is pressing up against the tilted pads. So when the machine is stationary, the tilted pad and the rotating collar may actually come in contact. But once that collar starts to actually move, the pad will tilt and oil will be wedged between the surface of the pad and the rotating collar. And this oil wedge will lift the two surfaces apart so they will not come in contact. A point to note is that On each of the pads in either of the bearings, the leading edge will be rounded. And what that rounded leading edge will do is it'll actually encourage oil to get pulled up and in between the pad and the rotating collar. And there's a bit of a similarity between that rounded leading edge and also the rounded edges of oil grooves in sleeved bearings. They serve the same purpose. It's to help pull or draw an even surface of oil into the bearing. When you look at the Mitchell bearings only work in one direction. The pad tilts in one direction, and that's the only way that that bearing will effectively be a thrust bearing. Whereas with the Kingsbury, the pads are tilted and they're rounded on both edges. So therefore, with a Kingsbury bearing, it can be operated in either clockwise or counterclockwise. Ball and roller bearings are referred to as anti-friction bearings. Anti-friction bearings have very, very little resistance to friction due to the rolling motion of the elements. There's some different styles of anti-friction bearing. There's the ball bearings where the actual rolling elements are round balls. They're spherical balls. You have a roller bearing, and in the roller bearing, instead of having spherical balls, they're like little drums, if you will. They're rollers. So those rollers are the rotating element. You also have needle bearings. Needle bearings are very, very thin, long rollers. And you also have tapered roller bearings. In the construction of a anti-friction bearing, you have the outer race, and you also have an inner race. And between the outer race and the inner race, you have your rotating element that could be ball or roller or needle or tapered roller. And those rotating elements will actually be spaced apart by a cage or separator. Anti-friction bearings have an inner race and an outer race that are hardened, highly polished surfaces. The rolling elements are also very smooth and highly polished and hardened. So the primary function of a lubricant in an anti-friction bearing is to prevent corrosion, to protect those highly polished. Bearing seals are made of felt, synthetic rubber, or leather rings. And what bearing seals will do is keep the lubricant in and keep contaminants out. So when you have ball or roller bearings, they can be already closed, meaning that their lubricant is inside and the seals have been put on to seal the bearing. So when you hear of a sealed bearing, sometimes they're referred to as lubricated for life. So no additional lubrication is needed. They're lubricated at the factory for the life of the bearing. In anti-friction bearings, either oil or grease can be used as a lubricant. And the primary function of that lubricant is to prevent corrosion and protect the highly polished surfaces. The lubricant will also seal and keep the dirt out. It'll also remove heat and reduce what friction there is in the bearing. So when should oil be used over grease? Oil should be used where the resistance to motion must be minimized, or where the speeds are high and the grease will cause too much internal friction. When there's going to be high operating temperatures, use oil. And when there's also going to be low ambient air temperatures, use oil. And when should you use grease? Grease is less likely to get flung out from the bearing, so when there's a chance of oil getting flung out of the bearing, you may want to use a grease. Also, grease gives a better seal than oil. And also, grease being stickier than oil will give you better corrosion protection during long idle periods. When it comes time to greasing a bearing, there's a few things that you should be aware of. And the most common killer of a bearing is over-greasing. So, before you do go and grease anything, make sure you have the correct type of grease for that type of bearing you're going to be greasing. Make sure it's rated for the right speed, the size, and the environment. And also, do not over-grease it so If the bearing is greased, it may be done by the number of operating hours, or there may be some other reference that you're using to how often to grease. There are web-based calculators to help you find what kind of an interval to choose. So if that's the case, go to the manufacturer's website, find out what they recommend for your application. And how much grease do you need to add? Again, you don't want to put in too much, and you also don't want to put in not quite enough. So you want to get that Goldilocks amount. If the manufacturer gives a recommendation, follow it. And lastly, don't mix up different greases. Now that you're ready to actually start using a grease gun, you'll make sure that you do have the correct type of grease for the machine you're going to be greasing. Before you start greasing any points, clean the grease nipples. You don't want to be injecting dirt into the bearings via the grease nipples. So before you start, clean all your greasing nipple points. Also, the grease gun that you're using, clear the end of the grease gun applicator just a couple shots to purge any debris off of it. If there are drain plugs for the grease points that you're going to be greasing, remove the drain plugs if you have them. Then connect your grease gun onto the nipple and put in the correct amount of grease. In some cases, it may be the number of pump strokes that you're going to be putting in. Sometimes you can use a vibration meter, and what you can do is put in the grease until the vibration level drops down to its normal baseline. That's when the bearing has just the right amount. And after you've done your greasing, allow the equipment to run for a while to allow any excess lubricant to be released, and then put in the drain plug after. And once you're done, clean off the excess grease off of the nipples. And be very careful if the piece of machinery is actually in service. Be careful of loose sleeves or any loose jewelry. Tie your hair back. You don't want to get caught. With automatic lubricators can dispense oil or grease. There are a number of automatic oil dispensers in the plant downstairs. In an oil lubricator, the reservoir will release just enough lubricant to maintain the level inside a gearbox or inside a oil reservoir. For cleaning bearings without dismantling a bearing, before you start, you want to clean the dirt from around the outside of the bearing housing. Then remove the end covers, spray some solvent to flush out the old lubricant and all the sludge. Once that's done, spray in some light lubricant and then refill the bearing with your normal lubricant, either if it's oil or grease. When it's not possible to remove the end covers, remove the drain plugs and drain out the oil. Then refill with solvent and run in a short time without any load. Then drain and flush out the solvent with some fresh light oil. And just keep doing this flushing with light oil until you're happy that all the solvent has been flushed out of the bearing. So then drain off your light oil, fill the bearing with your normal lubricant, and put it back in service. The best way to clean a bearing is by dismantling it. So you want to remove the bearing from its shaft and use a bearing puller or a brass drift, and be very careful when you're removing a bearing and only apply a force on the races. Do not apply force onto a race so that the forces will be transmitted through the actual rolling elements of the bearing. So once you've removed your bearing, let it soak in solvent for 12 to 16 hours. And remember that for your government examination. When you want to clean a bearing by dismantling, let it soak in solvent for 12 to 16 hours. What you do in the real life may be different, but for your examination, that's the right answer. Okay, so after your bearing is soaked, all the old lubricant and sludge should be removed. Take the bearing out of the solvent and then immerse it into some light oil. And then when it's in the light oil, just rotate it by hand to coat all the parts. Once the bearing is coated in light oil, take the bearing, hold it in your hand, and rotate the inner and outer races and feel if there's any roughness. If you notice any roughness, the bearing will need to be discarded. Never use compressed air to blow out a bearing. If you do use compressed air, it'll have a sandblasting effect on those highly polished, hardened surfaces, and it will reduce the life of the bearing. After a bearing has been cleaned and lubricated, have a very good look to see if there's any pitting or flaking going on in the rollers or in the races. Also, look at the rollers or the balls and see if there's any pittings or cracks. Look for corrosion, and also look for any signs of overheating. If there is discoloration from overheating, it'll show up as a blue color. When installing a bearing, the shaft must be absolutely clean. So before you install a bearing, clean up the shaft, make sure there's no burrs on it or corrosion, and coat the shaft with some oil. And then when you're installing the bearing, you can use a press or a piece of pipe of the right diameter, so that when you start to either press or tap the bearing onto the shaft, all the force is going through the tube into the inner race of the bearing. That way the inner race, there's not going to be any forces transmitted through the actual roller element. When a tight or press fit is required, a bearing can be heated to expand it evenly, and actually it makes it easier to put on. So if you are going to be using a heat to install a bearing, use a bearing heater, an oil bath, or a steam heater. And you want to make sure that the bearing does not go above 100 degrees Celsius. So you want to get into the ideal temperature range between 80 and 100 degrees Celsius. Be careful not to overheat the bearings. That's a really good way to shorten their lifespan. So do not use a direct torch or any form of heating that you cannot regulate. When applying grease to a bearing, how much grease do you put in? Up to 1/3. Never put more than 1/3 of grease into a bearing. If more than 1/3 is put in, that's going to cause excessive internal fluid drag and cause overheating. 5 causes of bearing failure: poor quality lubricant, incorrect lubricant, or old lubricant. Improper fitting. During an installation of a bearing, if force is applied through the rotating elements during assembly, the inner and outer races may be damaged. Also, the rotating elements can be damaged. In extreme cases, you can have indentations in the races caused by forces going through the rotating elements, and that's known as brinelling. Another cause of bearing failure is misalignment. If the machine's shafts are not aligned correctly, it can have a lot of stresses put onto the bearings, and that can manifest in failure. You can also have false brinelling. Now, the difference between true brinelling, that is caused by forces going through the races and making indentations in the races, and false brinelling, which makes indentations also in the races. False brinelling is caused by vibrations. So what's happening in false brinelling? Indentations of the balls and rollers are being transferred into the races by vibration. The last cause of bearing failure is high operating temperatures. The maximum temperature range that we want to have a bearing generally go up to, the highest, 65 to 70 degrees Celsius. That should be the highest unless you have a special application. That's all, folks. For the lubrication and bearings, make notes, review the material, and there'll be a few links posted on the Learning Hub of some YouTube videos that are really good on explaining these topics. Thank you.